talking very loud. You're like one of those people that can't whisper. Like, oh my god, yesterday. Don't you want you too? I don't know what I'm here.
Okay.
I have missed
Chapter
like
15,
10
which
classes
is
in a row.
so very
He
good.
called me out on it.
Mechanical wave, there are two types of yes.
He was like, did he drop the shit? I'm like, no. He said, he hasn't been going to
How many questions can we expect to be trying on the final?
Say it again.
How many questions can we expect?
Well, I'll do it on next Thursday. And the next class. Not next Thursday, but next class. Okay.
I can't whisper, you're right.
There are two types of mechanical wave. One is called longitudinal. Another one is called transverse. Longitudinal means the propagation, propagation along the backwards. What is it? Vibration. The other way around actually. The vibration along the propagation. What it means is, if you have a spring, alright, and what you do is you squeeze few of them. You squeeze. You squeeze here a little bit, and when you leave it, what happens is this goes like this. Can you see my finger rolling? Right? Let me repeat once again. This is a spring fixed at two ends, and you we squeeze few of the ring, squeeze it. I'm squeezing, right? If you squeeze and then release, what happens? Then they try to go back, but that this will push this, and this goes here again. It goes like this. Right? It's like a motion of earthworm. So in this case, the wave is traveling this way. The velocity of wave in this direction on the positive x, let's say this is positive x, and your vibration also along positive x. The velocity of the wave is also traveling this way. The vibration, if you look at my finger, this is the vibration, right? Vibration also along the x-axis. So when the vibration and the propagation is in the same direction, that kind of wave is called longitudinal wave. This kind of wave is called longitudinal wave. The transverse wave is the vibration in the direction perpendicular to the propagation. What it means is, if you throw a rock in the still water, what happens is the water ripples like up and down. Is that right? So the vibration here is up and down, but the wave travels in this direction. The velocity along x, positive x plus x. But vibration, this is the vibration, right? Vibration perpendicular to propagation. So vibration is this side, wave is traveling this side. Are you following? So wave is traveling along x. Both the case, wave is traveling along x. But in this case, vibration and the propagation is along the same direction. Right? Both the cases, wave is traveling along positive x, But in this case, vibration is along the same direction of x. In this case, the vibration is in the perpendicular direction of x. Does it make sense? So this type of wave in which the vibration is perpendicular to the propagation, such type of wave is called the transverse wave. This is called the transverse wave. The another example of transverse wave is you tie a string on one end, the other end with your hand you just move this up and down, alright? Then what happens is the string goes like this, right? If you move your hand up and down, then what happens? The wave travels along this direction, but the particle moves only up and down, alright? So this is another example of transverse wave. Mostly we will do only transverse wave. We will not discuss much about the longitudinal wave in this section, alright? There are a few problems of the longitudinal wave in your book. You can do it, which is pretty simple. You need to calculate only the frequency or the angular speed or the velocity. Those are pretty simple things. But I don't think I'll ask anything related with the longitudinal wave in the test, okay? But the transverse wave is another beautiful thing because the wave in this particular mechanical wave, the wave travels in one direction, the vibration is in the other direction, right, in the perpendicular direction actually, and that does not depend only on time but also on position. That is the beauty of this mechanical wave. I know it sounds a little complicated, but before doing that, let me recall. This is same like simple harmonic motion, the one that we discussed. This is also simple because what you do is, let's say you are moving your hand front and or let's say you have a simple harmonic motion here. The string is tied at one end, and then this end moves up and down with simple harmonic motion. Now what happens here is, as it moves in simple harmonic motion, that will create a wave in this string going up and down. Okay? So basically this wave is another way of the wave which can be explained by simple harmonic motion. Okay? Right? Yes, because this is moving with simple harmonic motion up and down, and that creates a wave. Alright? So in those cases, I just want to recall something called frequency, which was what? 1 over time period, right? Time period, what is time period? One complete cycle, is that right? Time period is one complete cycle, frequency is 1 over time period. Omega was 2 pi of the frequency, is that right? What else was there? What is it? Amplitude, okay. Amplitude is the maximum displacement. Amplitude is what? Maximum displacement. Velocity, okay. What is wavelength? What is lambda? What is it? Distance from peak to peak. This one is called lambda. Okay? From this peak to this peak. Or one complete cycle. You can take it from here to there also. This is one complete cycle, right? So you can say this one also, the same thing. If you take it here, then you have to add this part. So distance between crest to crest or trough to trough, right? That is what we call wavelength, which is called lambda. Okay. Oh, one beautiful thing. One beautiful thing. if I say velocity, velocity is what? Distance over time. Is that right? Is that right? Velocity is distance over time. If I take time, what is time period? Time period is to complete one cycle, right? So time period to complete one cycle means from here, it goes here, that will be one cycle. So now it repeats again, isn't it? Right? So this is one complete cycle, that is time period. What is the distance to complete one complete cycle? What is it? Lambda. So if you cover lambda distance by time is what? Time period, which is t. So velocity is the beautiful thing, which is simply what? Lambda divided by t. Right? Or velocity can also be written as, what is 1 over t? Frequency. So I can write here lambda times f. Is that right? Because 1 over t will be f. Right? We can play around a lot of things here. Time period is what? Time period is 1 over frequency. Frequency is what? 2 pi by omega, right? Frequency is 2 pi by omega, because frequency f is omega by 2 pi, right? Isn't it? Omega by 2 pi, denominator of denominator was numerator, so it will be 2 pi over omega. So you can play around. So the relation between frequency, time period, omega, velocity. Remember, this velocity is the velocity of the wave. Velocity of the wave. This is velocity of wave. Okay. So now let me have a little bit of fun. Okay, now look here. Look the beauty. Look at the beauty here. This is my wave. This is my displacement. When it goes up and down, I want to make a big diagram, okay, big figure. So this goes like this, like this, like this. Oops. Maybe. Okay. This is my x. Now here's the beautiful thing, okay? This is my x, and this is my y. Now let me do it here. This is my y vertical direction. This is my 0. Okay? This is my 0. If this is my simple harmonic motion, if this is my simple harmonic motion, then my y, look, here's the beauty. Here's the beauty. Y is a function of x and t. Listen here. This is, let me go back to this. Let me go back to this page. Look at the beauty here. This is different than chapter 14, because if you see a ripple in the water, right? If you see the ripple on the water, it is not a fixed wave. The thing is, if you put a certain object or flower, that flower just goes up and down, isn't it? Wave goes towards the end, but the particle moves only up. Particle will not move, it will stay there. Did you understand? Did you understand? So in other words, let me make this. If I move this here, what happens is, let me use another ink. I don't know if you can see the another ink. If I move it here, the wave actually goes something Hello. Something like this. Right? Right? Because my particle moves from here to there, and then the wave moves something like this. If my particle goes from, keeps on moving, let's say it is here, alright? If it's here, then it may be something like what? Something like, I don't know. Or maybe somewhere here, right? What did I make it? Actually, this goes something like this. I'm making it quite exaggerating. Anyway, if I bring it somewhere here, then this goes something like this. Are you following me? Right? So now what happens here is, if I say, what will be the displacement at this point? What will be the displacement at this point, let's say, or let's say at this point? Then there are three things. At what time? Let's say this is at time t equals to 0. At time t equals to 1, you have here. At time t equals to 2, you have here. The point at x equals to 0, at time t equals to 0 will be maximum. That's what we call amplitude. Alright? So my equation y at x equals to 0 and then t will give me a cosine of omega t. This we did earlier. Right? This we did earlier. I put here x equals to 0 because this is my simple harmonic motion. When it goes up and down, then this is my simple harmonic motion which we already know. Did you get this one? Right? But the beauty here is at time t equals to 1, the position this is already here. So let's say at x equals to 1, this wave was here, but at t equals to 0, x equals to 1, the wave was here. At t equals to 1, x equals to 1, the wave is here. Did you get that? So at t equals to 0, x equals to 0, wave is here. Y is this much. At t equals to 0, but x equals to 1, x is 1, at this one point from the center at 1 centimeter away, the wave actually is here. The y displacement is only this. At x equals to something, the y displacement is 0. Right? At t equals to 0, y displacement is, at x equals to this point, the y is 0. At the same t equal to 0, at this point actually the y is down. Alright? So the wave is not only function of time but also the function of position. At time t equals to, like let's say after 2 seconds, but at what point? That's the question. Alright? So this is a pond, this is a lake, a big lake. When you throw a rock here, let's say it's at the maximum point, it's the opposite. So now the point here is, the wave is like this. Let's pick at this, your flower is here. Now what your flower does is, the flower at t equals to 0 will be here, but at t equals to 1 will be here, and at t equals to 2 the flower will be here, and keep on going down, so flower goes down, and keep going down, the flower will be 0. Alright? And then it moves up and down. So the particle, every particle is moving up and down, alright, but at different time. So the point here is, it is not only a function of time, but also the function of position. The point here is, the particle at a certain point from the origin, at a certain time, another time will be different. Are you following? So the y, the displacement y, depends on what particle first of all? which particle, and then at what time. Yes?
This graph is position against time or position?
This is the position.
Okay.
Y displacement, vertical displacement versus position. Which is also, position means, well, Y displacement is this, right? The position is from the center, how far? Are you following? Because the wave is going like this, the wave is moving up and down, right?
And then the T's just represent?
T is the time at what time? This is the fourth dimension. Actually, this is the four-dimension problem. This, by the way, there is only x. Actually, it's not only x. There's x, y, and z. All right, we are taking only one direction, only x. But in reality, it goes x, y, z. All three dimensions there, the space, and then fourth dimension is the time. So the question here is, at what point and at what time? All right, the same position can have zero displacement. The same position can have maximum displacement. The same position can have minimum displacement depending on what time. The same position is zero displacement at 1 second. In 2 seconds it can have maximum displacement. At 0 second it can have minimum displacement. So the same position will be up and down. At one time it is here, at another time it is here. Did you get that? So that's why it is so beautiful, because it is such a wave that it's not a fixed wave, but even the particle is moving up and down. So wave is also going, and the vertical displacement is also happening there. So it is space and time problem. At what position and at what time. So that's what it makes you so beautiful. So here, the interesting thing is, but look here, the interesting. The wave travels to the, well, this is on the right side, okay? To the right, in time, let's say, if you have an x displacement, so x divided by velocity will be your time, right? Because your velocity is x by t. This velocity is velocity of the wave. All right, velocity of the wave. So you don't put y. This is not y. Y is this one. You have x. So x is the velocity. Velocity is distance by time. Distance along x direction and time on that time. So what it means is your time is x over v. So in other words, at this time you have x over v in another time. So it means the wave at this point or another point would have the same as it was t minus x by v. So so I can write the displacement straight away. Y, if I put like xt, then my a will be cosine of I'll have omega t. Oops, let me do this. Omega t minus earlier, which is x by v, which is because of the displacement. So this will be my real function of real y displacement at x distance at t time. If you understand this one only, then you are good. If you really don't understand, just memorize it. I have no choice. Alright? Actually, it's a beautiful thing. So that time is this time. That time is this time. But if you look at the position here, this position is same as this position, right? So at this distance, this would have been the same displacement as it was x over v time before. Are you following? Does it make sense? So this displacement would have, because from here to here it takes what? X over v time, isn't it? So from here to here it will be x, excuse me, from here to here it would have been x over v time. So in other words, this position would have been same as if it was t, and then minus x over v will be the same thing. Say it again. Which one? V is the velocity. I gave you the velocity of the wave. Right, of course, V. What is it? V, lambda f. Because V equals to x over t.
I don't know what's going on. I'm really confused. Like, I'm trying to look at it, but like you have all these lines that says t equals this, so you're basically saying possibilities instead of like I'm just confused. I'm really trying to follow.
Right. So this is the I don't blame you. I don't blame you.
The initial explanation wasn't that hey, it's in three dimensions. You just do t's. So like where are these coming from? That's a y. And that's a
Right. So here. Okay. Let me make sense one more. If you look at the wave ripple, just think of the wave ripple. All right. The same particle goes up and down at the same point. You pick one position wherever you want. If you pick one position here, let's say, actually this has y displacement three things. In this particular figure, let's pick this point. If you want to pick this point, let's say, which is x equal to this much, this x can have, depending on your time, this x can have either this position if it is on red, or this position if it is another one, or this position if it is another one. Are you following? So in other words, at one time it will be here, at the other time it will be here, at other time it will be here, because it is going up and down with t. But this is at a distance x. So basically it has what? X also and then time also. Same position can have different values at different times. Regardless of, it means, let me go back the wave which we discussed in the last class. Right? This is a simple wave. This was not bouncing up and down. This is a real, which is on time. Is that right? So this one was, let's say, we use like cosine of this, right? This one was your amplitude. Right? So your y equals to straight away a cosine of omega t, because it was simple. Omega t is basically theta. So your y was a cosine theta, because the particle doesn't move. This only goes in this way. The wave only travels here fixed. This is not going down. Are you following? So in this case, at this time you have only this, no problem. This time you have only this, there's only one. At this time you have only one y. This time you are fixed. This wave was fixed. But now, the wave is not fixed. This is not traveling this. This is also going down, so this is going, the same position will be up and down. So this vibrates down also, up and down also. So that what it makes like space and time two different things. So in other words, your y will be this. Does it make sense? So if you, well, this is just the flashback, so you don't need this, alright? This is the recall. This is the recall. So now, this pencil is killing me. Alright. Now, once you know this, all you have to do is just simplify this. Let me copy that one. So your y is function of x and t both. Your both are variable here. X is also variable, time is also variable. Two variables. Okay? So you have a, which is the amplitude, times cosine of, let me copy here, omega t minus x by v, right? Can you see this? Okay, yes.
So that t minus x over v is the change in time for like a possible graph?
It's called phase. Well, you're right, I know, but it's called the phase. Phase meaning, remember last time when I discussed about the phase, right? So what it means is, at time t, but x equals to 0, it was here, but since it moves at x by v time, to give same, it has to be back to x by v before, then only it gives the same point. Then it will be, does it make sense? So it's basically leading. Your x by v is leading, that's why you need to do it minus, because at minus is the time, yes, because at x point it's already x by v there, but when it travels there, it will be same as it was t minus x by v time, it will happen the same point. Did you get that? Okay. Alright, so, well, the solution will not be that hard, I know. To understand this is pretty complicated, I don't blame you, right? It is a real kind of fun, but can somebody help me? If I want to replace this omega, what is omega in terms of time period? 2 pi divided by t, very good. So cosine, this omega I replaced by 2 pi divided by t, and then I have this lowercase t. Right? Now, can somebody give this v? By the way, let me do one more thing. There is something called wave number. Okay, where do I write down? There are two things. I'll plug it here. Okay. Time period t is what was the time period? 1 over f, right? Isn't it? Time period t is 1 over f over 2 pi over omega. Right? There's another one called wave vector. This is wave vector. Wave vector. This is 2 pi over lambda. Meaning, how many waves per lambda? How many waves per meter? Alright, this k is how many waves per meter. This t is, what's the time per one cycle? Isn't it? Which is 2 pi, so you have to divide by omega. This one 2 pi will divide by lambda. So these two identities, so in other words, what I'm trying to do here is, your v is, didn't I draw v before? V is lambda divided by t, right? Oops. Can you recall that? V equals to lambda by t? Okay. So what I'm trying to do here is, I'm trying to convert this v, lambda over t. So this lambda goes here, t goes there, right? So minus, and then this x will be, this v, I'm trying to convert this, I'm having a mess here. Okay. I'll put x there, alright. Oops. How do I show this, the whole thing? Okay. Can you see it? Can you see the whole thing now? Okay. I put here x, alright. I put here x, and then in place of v, I use lambda by t. Did you get that? Right, x, and in place of v, I put lambda, because v is denominator, I can put lambda over t there. Okay? So, now, what I'm going to do is, I want to multiply this inside. So what it will be is a cosine. Let me leave this 2 pi outside. I replace this inside, okay? So this will be what? T over capital T minus, T and T will cancel, right? X over lambda. So this will be y of xt. So this will be my final expression for the displacement y at this time, at this point. Alright? This can also be written as, by the way, since cosine of any angle, cosine of theta is cosine of minus theta, right? Are you following? So I can simply switch this front and this back. It will be the same thing. So y of x of t can also be represented as a cosine of, I use 2 pi x divided by lambda minus t divided by capital T. Remember, this is a variable, this is constant. This is variable, this is constant. Alright? Lambda is fixed, x is my variable. T is fixed, time period is constant, but little t is the variable. So this is my expression for our, either you can use this or this is the same thing, because cosine of minus theta is same as cosine of theta. So it doesn't matter whether you put one side on the left or the other side on the right, on the minus. Okay, so or y of xt can also be written as a of cosine of, by the, what is 2 pi by lambda? What is 2 pi by lambda? K. What is 2 pi by t? Omega, right? Okay. Omega t. You can also write in this way. Okay. So I'll make it here because, let me recall, because I'm making a mess here, because 2k equals to 2 pi by lambda, and then omega equals to 2 pi by t. So these are the two identities that we use to find this expression. Okay. I know we're getting a little bit harder and harder. I'm trying to make it a little easier. Okay. So let me go to the bottom line. Y of xt equals to, we got it what, a cosine of kx minus omega t. By the way, this was the case, let me bring it here. This was the case if the wave was traveling on the right, isn't it? Because I put here minus x over t, because that minus x over t would have been the time it was before, because when you travel there, the wave peak travels up to here. So this time, this peak was t minus what it traveled up to here. So at this point it was this amplitude. So in other words, since the wave was traveling on this side, my time was minus x over v. Alright? But if the wave was traveling on this side, I should have added this, isn't it? So in other words, this was wave traveling in plus x direction. But if the wave is traveling on the negative direction, then it would have been y of xt. I don't want to redo all those things. I already gave you a lot of trouble anyway, especially at least one of the students. So, alright. So now I just write here, oops, cosine of, it would have been kx plus omega t. This one is traveling in negative x direction. Okay? So just remember, if it's like minus omega t, it means the wave is traveling on your right. If it's plus omega t, then the wave is traveling on the left. That's pretty simple. And one interesting thing, okay, one interesting thing, since, again going back, I don't want to explain too many things. Again going back, every time that kx minus omega t, these things remain same, because if the wave travels kx distance, then omega t at back it would have been the same thing, meaning if it is peak here, right, at 0, then your distance is here, right? So if it goes there, then this would have gone here, so this will be the same distance. So if it goes here, it will be the same distance. So every time that kx minus omega t is constant. Are you following? So in other words, I'm not going to explain too much. Your kx minus omega t is constant. This is called phase. So basically your phase is constant. So whatever is your distance between two corresponding peak, those travel together. Now that peak, if one moves like 2 meters, another also move 2 meters. That's what the wave travel is. Alright? So in other words, this phase is constant. So if I do derivative with respect to time, this one, I get what? K is constant, right? I'll keep this out. Dx by dt minus omega, right? Because dt by dt is 1 equals to derivative constant is, what is it? 0. Where is it? Come on, 0. It's pretty simple. So your dx by dt equals to your omega goes on the right, k goes down. So basically, what is your dx by dt? Is the velocity. Velocity of what? Velocity of the wave along where? On the positive x-axis. Equals to nothing but omega by k. This is another expression. So are you following up to here? Up to here it's okay, right? More or less. There's another one called wave equation. How you get wave equation is, how you get the velocity? Let's say, let me go back to the same equation. Alright? All we know so far is y of xt is a cosine of kx minus omega t. Is that right? Is that right? Now, if you want velocity, what do you do? If you want velocity, what? Divide by what? Divide, right? You do the derivative with respect to time. Very good. If I want velocity along y direction, remember the velocity, the wave is traveling again. Look, the wave is traveling here, up and down. Alright? Because this is your y. So this is your displacement. So your velocity of the wave in the y direction. That's what I'm, well, in this case it's going down. So velocity of the wave in y direction. Alright? So the velocity along y direction, xt. What you do? You need to do the derivative with respect to time, right? But the problem here is, if you need to do derivative with respect to time, there is not only time variable, there is another variable x also. Position is also variable, right? So now what do you do? Partial, right? So you need to do partial. You cannot do the full derivative, okay? Partial derivative of y, which is a function of x and t both, you do partial with time only, keeping your x constant. Alright, a little bit of calculus here. So this will be a of, what will be this? What will be this? You are doing with time. What is your time? Time is here, right? Isn't it? Time is here. So what happens here? Minus omega comes out. Is that right? And cosine of this derivative is what? Sine of what? Kx minus omega t with a negative sign. That negative makes it plus. Remember the difference between last one it was a cosine omega t only with a plus. That's what it would have been minus here, minus a omega sine of this. But now the omega is negative, that's why it becomes plus here. Okay? What about your acceleration along y? You do derivative again? Is that right? So what it will be? Minus? What is it? This will be, let's say, d square y, which is function of xt, divided by dt square. This will give you minus a omega square cosine of kx minus omega t. Now a cosine kx minus omega t is same as yxt, right? So basically d square y of xt divided by dt square, equals to minus minus a, and this guy will make you y. So minus omega square y of x and t. Did you get this one? But let me ask you this question, okay, as a theoretical question. Okay, now let me go back here. This is about the doing derivative with respect to time, partial derivative with respect to time. Let me go, because there's another variable, not only time variable, there's another variable which is what? Which is the position, which is x. Alright? So now what about dy of xt with dx now? Remember here, it's x. What it will be here? K here, right? Is that right? So coefficient k comes out, a is there. A is there, k will be out, and cosine will be sine kx minus omega t. You are doing with x, so this is constant. So I leave it like this, only the coefficient of x comes out, which is k. But the derivative cosine is sine with a negative sign. Did you get that? Did you get that? Yes. Uh-huh. Uh-huh. No, that turns to 0, of course, why not? That's why you don't have it, that's why you have only k. Actually it's k minus 0. Yeah. Uh-huh. Okay. So now if I do another derivative again, but I don't have a name for x, alright? Because if you do the derivative with time, I could have written here acceleration along y. But I'm doing with respect to x. Now I cannot call it acceleration, by the way, because acceleration is derivative with respect to time, not with position. Alright? Yes, you have questions? Second? Oh, okay. Okay, alright. So now look at the beauty here. So if you do the second derivative once again, d square y of xt, and then dx square, this will be what? Now you are doing derivative once again. So derivative sign will be cosine, right? And then you have x here, so this will be minus a, and then what is it? K square, right? Because one more k comes out, derivative sign is cosine, and then it is kx minus omega t. Now again, a and cosine will be what? So d square y of xt divided by dx square will give me minus what is it? K square y xt. Beautiful. Beautiful. Now what I'm going to do is, I want to combine this, I call it equation A, this I call equation B. Oops. Okay. Now can you solve equation A and B? What you do is get rid of y, x and t. What you can do is you can divide equation 1 by equation 2, or equation A by equation B. So when you divide it, what happens? D square yxt by dt square divided by d square by dx square will be, yxt will cancel, you will left with omega square divided by k square, because minus will also cancel. Is that right? Did you get that? Okay. Now what I'm doing is, I'm dividing, or make your life easy. You just replace this y of xt, which is this divided by k square, right? Is that right? or y of xt is what? This divided by omega square. Is that right? Did you get that? So what I'm going to do is, okay, I'm going to copy this. Okay, never mind. D square y of xt divided by dx square equals to minus k square. I leave it there. But in place of y of xt, I write here this divided by omega square. Is that right? Is that right? So this one will be k square, and then this one will be, if you see there, d square y of xt divided by dt square times 1 over minus omega square. Is that right? So minus will cancel. So what I have here is d square y of xt divided by dx square, minus equals to, minus will cancel. This will be k. Can I borrow one pencil? It's almost 12 already. Thank you. That's much better. Okay. So k square divided by omega square, right? And then this is d square y of xt divided by dt square. dt square. By the way, what is k square by omega square? Omega by k was v, right? Because we, 1 divided by v square. Because this one was what? V equals to omega by k. But k by omega is 1 by v, right? So this will be 1 by v square. So d square y of xt by dx square equals to 1 over v square partial of y xt by t square. This is what we call wave equation. So if I ask a theoretical question, something like, well, derive a wave equation. So all you do is, you can start straight with from this equation, general equation, and then you just, yes.
Go back to the question here. Because you were pointing at the formula.
Oh, the displacement along y-axis can be explained by this equation, right? Where k is wave vector, omega is the angular frequency. So from here, all you do is do partial twice, and then partial with time twice, and then partial with x twice, and you just get to equation, you simplify it. It's pretty simple, so it doesn't be that hard, all right? Okay, I have only 15 minutes left. I'm not going anymore. You can do it. Just review. You have notes, right? Yeah, just review. You'll find out. Yeah. You should be able to. You should be able to. Okay, so let me move ahead. Oh, by the way, the problem 15.1 is too easy for me to do it for you, because you have the formula V and F, you have your frequency given there, velocity given there, frequency given there, find lambda, just put V by F. It's too easy. You can solve that. You can solve this equation 15.2 yourself, because all your formula is a cosine of x by lambda. This formula is there. At a certain time, at a certain lambda, your lambda and time is given. So you can find, you can just plug the expression, you can get this easily. Alright? You can do this. This is the one I just derived it for you, which is called the wave equation. Alright? 1 over V. And 15.4, okay, let me finish this 15.4, which is another beautiful thing. Okay. When the wave goes like this, actually what happens there is, for the wave, You have your force on this direction. Excuse me. You have your force on this direction. The particle moves off like this. So let's take at this point, you have your maximum, this your velocity along y, velocity along y. This will be velocity here, small, this will be a little bit small, this will be a little bit, this is 0, right? This is how the velocity increases. And you have your force along y here, alright? So one force is pulling this way, another force is pulling this way. So if this is your another force, and if this is the wave velocity v, then at time t, this will be your distance, the wave travel from here to here. But at the same time, the vertical displacement, if your vertical velocity is vy, the same time, the wave travels from here to here, but this particle moves from here to here. So this distance is your y, which is vy times t, and this distance is your x, which is v is the velocity of the wave times t at the same time. So the transverse what is impulse, by the way? What is impulse? Is momentum. Very good. Yes, right. Transverse momentum. Momentum. Yeah, I'm glad that you recall it. The impulse is momentum. What is the transverse in impulse means what? Force times. What is impulse? Force times time. Right? What is the momentum? Mass times what? Velocity. Very good. Velocity along y. Is that right? Did you get this? But what is your F? What is your F? F is the force, right? So force will be, let me go here. Okay. So force is, well, let me do it this way. This book has done a little bit differently, so yeah, I want to go this way. Okay. Yeah, the book has used this distance, well, this impulse and this impulse to F, which is V times T, and then this has divided, well, what did it do? Okay, they divided, okay, never mind. So this will be, no, T, F by V, plug it T there. So let me do this way, okay, in the book way. So T is F by V, and then Fy times F by V will be M times Vy, or how did you get that? Fy times T is Fy times T. Wait, just a second. Let me Fvy over V. Let me see. Fy times T is anyway, so anyway, the point here is this force, this side, if you take this side, your force times time, right, will be mass times velocity, and then time, because force is mass times acceleration, which is v, and then by t, you cross the t there, and which is ft, and given by vy over v, wait. So if Fy, well, just a second, something is wrong here. So your transverse impulse, which is Fy over t equals to your F, and then Vy over V, F Vy over V, well, your T will cancel anyway. This, okay. All right, so let me get here. So my over m will be, by the way, there is a term called mu, which is mass per unit length. All right, so mu is m over L. All right, so this will be your mass equals to mu times L. By the way, I need to explain one more thing. Let me see if I can finish this. 10 minutes. Okay, let me quickly do this. Okay, so if you have a length of a string like this, the mass of this point, or the mass of the string, or mass of this particular point can be written as mu, which is mass per length. All right, per length. So what it means is, in case of a string, or the wave, what happens, you cannot take a particular mass of that particular vibration because you have the mass of the whole string, right? But what you do is, mass of the whole string per unit length you can get. So this mu, which is mass per length, this is very important here. So let me finish this up. This comes out to be your mass times velocity along y will be mu is mass per unit length, right? And that length by time will be velocity. So that velocity by time will be there. So you have to multiply by time to cancel this. All right. And this times you have, this will be your mass, and you have, this is your velocity along y. So let me repeat here. Okay. So your mass equals to mu times length, right? If your mu equals to mass by length, so your mass will be mu by length, right? If I divide both sides by time, if I divide by time here, I can multiply by time there, right? Did you get this? So now what it means is, mu is there, length by time will give me velocity times time. This is how this term came. So this is nothing but your mass. Did you get this one? So now from here what you get is f of Vy over V, f of Vy over V, f of Vy over V will be equal to Vy over V, and then there is time also, times t equals to mu V, t and Vy. Alright? So now what it means is, this implies here your V equals to, look here, your V equals to, you have your V and V squared. So this comes out to be square root of f over mu. F over this mu comes down, right? So because your Vy and Vy will cancel, V and V will give you V squared, T and T will cancel. Let me use the red ink, okay? I know I'm kind of rushing here. So what happened here? Okay, so V and Vy will cancel, T and T will cancel. You have mu here, F here left. This V and this will give me V squared. So F over mu will be there. So I'll take the square root. So basically your V equals to F over mu. So your velocity of any string depends on force per mass per unit length. So what it means is, so bottom line here is, let me rush a little bit fast. So let me V equals to square root of F by mu. In other words, I don't know if you have, oh, I still have 5 more minutes, okay. I'll do one quick problem, should be okay. So with that expression, anyone here who play guitar? One, no one. Okay, 2, great. So from this expression, look here. From this expression, what it means is, if you increase the force, what will be the velocity? If you increase the force, what will be the velocity? Increases, right? But if you increase the mass unit length, mass per unit length, alright, mass per unit, the force the velocity decreases, right? So if you look at the guitar or a piano, I don't know if you have really seen the grand piano. Behind is a jumbo. There are so many strings there. Some are short. Your high pitch, the strings are shorter. The low pitch or the bass are longer. So in your guitar, if you have not seen, go and see the guitar. There are 6 strings in general, normal guitar by the way. The lower one has the thinnest string. Alright? Thin string means what? Small string means what? Mass per unit length. Meaning 1 meter of length have less mass. Are you following? If you take the mass of the first string of a guitar, which is the smallest, alright? And if you see the 6th string, which is the biggest. Does it make sense? So now what it means is, the smallest one will give you high pitch. So if you play the smallest one, that gives you ting, 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 high velocity sound, alright? But if you go the 6th string, which has more mu, is a mass per unit length, alright? More mu, that will give you bass, dum, 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 something like that, okay? That's one thing. So on the other hand, there's something called tightening. You know, when you tighten the guitar, right? You tune up your tuning. So when you tune the guitar, you tighten it. Tighten it means what? You apply more force. More tight means more force. Alright? If you apply more force on the guitar, alright, if you apply more force, your velocity will be high. More you do tight, keep on tightening, and then it goes more and more frequency. Are you following? More and more speed. So what it means is, more force, your speed will be more. Speed corresponds to pitch, by the way. Okay? So more speed. If you have more mass per unit length, by the way, this mu is not mass per unit length, the one that I discussed here. Alright, this is very important. Mass per unit length. Oops. So mass per unit length is very important. So if you have mass per unit length more, then that will give you less velocity. Or if you want to increase your bass, more like more bass sound, you increase the thickness or the diameter of your string, make it more heavy. Alright? If you want to add the more pitch, then you have less speed. So here is one beautiful problem, 15.3. I know kind of I'm rushing, so it may be very hard for you to pick up, which I understand. But this problem what you do, you have here, I think, the mass of the string, one end of the 2 kilogram rope. You have 2 kilogram rope. This rope is 2 kilogram. The whole string is 2 kilogram. Remember in your formula you have mu. So this must also have the length. 80 meter deep. So this is the mass of the string. 80 meter deep is the length. So make sure you divide this by 80, then you get mu. So once you get mu, and then you apply, the formula F by mu. So you can get the so your mu, I'll write it once again. This is mass by length. This is the key. Mu is not the mass, but mass per unit length. If your string has a mass of something, but at the same time the string also has this much of length, then that's mass per unit length is what it matters for the velocity of the wave in the given string. Alright? So, by the way, there are 2 mass. In this particular problem, there are 2 mass. Which one mass has to be on the mu? Because there's another one. Where is it? The linear, where is it? What's that problem? Oh, okay, it's here. And the another mass, which is 20 kilogram mass, is hung here. Yes, exactly. So don't use this mass as mu, because this 20 kilogram is attached at the other end of the rope. So that 20 kilogram will help you to find the force, because mass times gravity will be the force, right? So basically, it is just like a guitar string, but guitar string you tighten on the right, but rather than tightening on the right, you have a string there and you hang a mass on the bottom. So when you hang a mass on the bottom, what it means is that mass times gravity will be the force downward. So it is like upside down guitar, alright? And instead of tightening your screw, you have the mass hanging there. Is that clear? So this problem is similar to the guitar problem, only upside down. In case of force, you use mass times gravity, and in case of mu, you use mass of the string and then divide by the length of the string. All right? Okay, with that, if you have further question, let me know. We'll stop up here. Up to here only, we will be dealing with the in your final. Oh, by the way, I should have done one more thing. Yes, Thursday I will not, well, I may do only one problem because this is a little important, but I don't know whether I do that or not. Otherwise, the Thursday whole day I will do only the review for your final because